Hello, I'm Jonathan Newton of Vodafone, and I'm Project Stream Lead for Access Architecture at the Broadband Forum. With me for this video is Jasvinder Singh from Intel, who'll be going through the actual demonstrations with you.
If you're a broadband user, service provider, or equipment supplier, then you already know how critical broadband has become. As a consequence, network operations such as software and capacity upgrades, load balancing or power optimization need to be performed with the absolute minimum of interruption of service. Achieving this, however, can be a real challenge on traditional statically configured broadband networks. And this, amongst other things, is why the Broadband Forum is defining an architecture for subscriber session steering, enabling a variety of service and network changes with zero disruption to customer broadband. This is our second demonstration video dedicated to subscriber session steering. We're going to focus on three key operational use cases that the steering capability enables. And importantly, we'll show this using a fully cloud-native disaggregated broadband network gateway, which is based upon the excellent Broadband Forum TR-459 standard, and we'll do all of this deployed natively on Kubernetes. Let's take a quick recap on a couple of important concepts in the session steering architecture. Here we have homes on the left of the diagram connected to an access node with a traffic steering capability, then a disaggregated broadband network gateway or BNG with multiple user plane functions, and then this is connected to the data network on the right, which will link the customer to, for example, the internet. Labeled with a 1 on the diagram, when a subscriber initially connects to the broadband network, their session is allocated to a subscriber group based upon policy and profile of that customer. Then they're dynamically steered to the user plane that supports this subscriber group. A subscriber group is really just a set of subscriber sessions that all share the same service and quality needs and can therefore be moved around the network as one entity. As labeled with a 2 in the diagram, the really great part is that we can now move these subscriber groups from one user plane to another user plane using a make-before-break process with zero packet loss. This efficient and hitless move of groups of subscribers underpins the use cases we'll be demonstrating. Now I'll hand over to Jasvinder, who will take us through the first demonstration showing this make-before-break process.
Hello everyone, my name is Jasvinder Singh. I am a software engineer with Network Platform Software Group at Intel. In this presentation, I'm going to demonstrate some of the interesting use cases that leverage Broadband Forum Working Text 474 subscriber session staging architecture. This is lab setup. It consists of 3 Intel Xeon Gold 6338M CPU systems, which have 32 cores per socket as specified in Intel Select Solution Forwarding Platform, one P4 programmable Intel Tofino switch with 64 100 gig ports, and one top-of-the-rack switch. We use an Ixia traffic generator to simulate the traffic coming from access and core network. Each server platform has 2 by 100 gig Intel E810 series network adapter that features dynamic device personalization technology to support frame classification of load for new protocols. 2 servers are assigned to run VPP-based BNG user plane instances. A single BNG user plane can provide throughput up to 25 gigabits per second, and we can scale up the throughput by running multiple BNG user plane instances on 32 cores available on each of the 2 CPU sockets. The third server implements 3 control plane components. First one is BNG control plane function that performs subscriber management functions. Second component is user plane selection function or UPSF. It anchors the subscriber session context to the BNG user plane instances based on operator policy. The third component is control plane for traffic steering function, which programs subscriber traffic steering rules on the TSF switch over gRPC interface. Another important component is traffic steering function, which is implemented on Intel Tofino P4 programmable switch. It forwards the traffic of the subscriber to and from the identified BNG user plane. For the demonstration, we use Intel Container Bare Metal Reference Architecture, also known as Container BMRA, to deploy and configure Kubernetes cluster. Container BMRA employs Ansible playbooks and Helm charts for auto provisioning and configuration of the production-ready Kubernetes cluster. It also helps in configuring networking features as required by the application. In the Kubernetes cluster, we have set up 3 nodes on Intel Xeon SP CPU systems. On one node, we deploy control plane functions, while other 2 nodes run BNG user plane pods. We use Multus CNI plugin to attach multiple VFs to BNG user plane pods. We also use SRIOV network operator to configure SRIOV CNI plugin and device plugin in the Kubernetes cluster. These plugins help in discovering and assigning VFs to BNG user plane pods. We also leverage IPAM plugin to manage IP allocations to VFs that are assigned to BNG user plane pods. Another pod shown here runs device configuration function, which programs flow rule on the NIC to enable packet switching across VFs attached with different user plane pods. In first demonstration, we consider a scenario when operator brings down one BNG user plane for an operational reason, and all the subscriber groups active on that user plane are load balanced across other user planes. This chart shows the sequence of activities that are performed when an active subscriber group is moved from one user plane to other user plane in make before break manner. And this sequence is repeated for every subscriber group that is moved to other user planes. Here BNG control plane and TSF control plane both have subscribed to subscriber group update message coming from UPSF. UPSF starts make before break sequence and first sends a subscriber group update message to the BNG control plane, which configures the subscriber group state on the desired user plane. Next, UPSF sends a subscriber group update message to TSF control plane, which configures TSF switch to send upstream traffic for the subscriber group over the desired network connection to the new user plane. Finally, UPSF sends the update message request to BNG control plane, which switches downstream path to new BNG user plane. Also, BNG control plane safely removes the subscriber group state from the original user plane and sends back the update message to UPSF. Here on this screen, we see Grafana dashboard that displays real-time information. In the bottom right panel, we see 6 active BNG user planes. Each user plane supports basic internet service and has got 630 subscriber sessions allocated to it. Bottom left panel shows subscriber groups associated with each of the active BNG user planes. One subscriber group contains 128 subscriber sessions. Top right panel shows subscriber traffic currently being received and processed by BNG user planes. In the demo, different amount of traffic is sent to these user planes. On the tester side, we use Ixia traffic generator that sends different amount of subscriber traffic to 6 active BNG user planes, which receive the packets and send them back after processing. On the bottom panel, we can see all the packets sent to BNG user planes are received back by the tester without any loss. Now I'm going to run a command to bring down one of the active BNG user plane for maintenance. As a result, UPSF will kick off make before break sequence and apply load balancing policy to evenly distribute the subscriber groups across other active user planes. Here we can see in the bottom right panel, one of the user plane is in updating state, and the subscriber groups are gradually being moved to other active user planes by following make before break sequence. You can see now all the subscriber groups have been moved and that user plane has gone into inactive state. The other 5 BNG user planes continue to process traffic of the subscribers allocated to them as shown in the top right panel. Now, if you look at the tester stats on the bottom panel, the tester is receiving all the sent packets without any drop.
In a traditional deployment, if we need to upgrade the software on a function such as a broadband network gateway that's carrying active subscriber traffic, this will generally result in a customer outage. The upgrade is therefore performed in the middle of the night and as part of a carefully managed program to update software across the network. And this really limits the number of software upgrades that can then be achieved through a year. Now we've shown that with subscriber session steering, we have the ability to move a subscriber group between user planes with no customer impact. We can next explore how this can allow us to upgrade the software of an entire cloud-native broadband network gateway with zero customer impact. All of this will be using the rolling update process that's built into Kubernetes. This will be a huge benefit to service providers who will now be able to upgrade software at any time without any customer impact, enabling a much higher cadence of new features, bug fixes, and security updates, and using an automated deployment methodology that's built into the Kubernetes platform.
In this demonstration, we consider a scenario when an operator likes to upgrade BNG user plane software. The process of manually updating the containerized application can be time-consuming and tedious. Therefore, we leverage Kubernetes deployment controller that performs automated rolling update process without operator intervention. During update process, all BNG user plane pods are replaced one by one with the pods of new software version without any service downtime. While doing rolling update, BNG controller application makes sure that an updated BNG user plane pod is running and is in ready state before start migrating subscriber group from its predecessor. Here we configure two parameters for fine-tuning updates. First is max search parameter, which is set to 1. This value indicates the number of pods that are created above the desired number of pods during update process. We choose this value to allow only one BNG user plane pod to be updated at any time. The other parameter, max unavailable, is set to 0. This value indicates desired number of BNG user plane pods available during update process. Here on the screen, we see Grafana dashboard. Table in the bottom right panel shows 4 BNG user planes in active state, and each user plane has been assigned 630 subscriber sessions. Subscriber traffic is currently being received and processed by BNG user planes as shown in top right panel. On top left panel, we can see all the 4 BNG user planes that are currently active uses software version 1. Now I'm going to apply deployment manifest file with new software version of the BNG user plane, and we will see rolling update process where old BNG user plane pods are replaced with new pods. Now we see Kubernetes rolling update process has been started. New BNG user plane with software version 2 appears in the table shown at the bottom right panel. Subscriber group that were previously attached to old user plane pod have been moved to new BNG user plane pod, and the old BNG user plane has been set to inactive state and marked for deletion. We also see all the traffic that were previously handled by old user plane is now received and processed by new BNG user plane. As rolling update process progresses, all the BNG user planes with old software version are replaced one by one with new BNG user planes. We see there is an increase in number of BNG user planes with software version 2 as shown in top left panel. If we look at the traffic chart on the top right, we don't see any interruption when subscriber groups are moved from old user plane to new user plane. At this stage, all the BNG user plane pods are updated and a rolling update process has been completed.
The next use case we can show enables service providers to match the capacity of a broadband network gateway user plane to the traffic demands on the network as they change through the day. The traditional way of building a network would be to permanently have enough BNG user plane capacity available to support the exceptional peaks in demand with some room to spare. These peaks are much higher than the daily average demand for capacity, and the difference between the average and the peaks is getting bigger due to the over-the-top streaming of large events such as sports finals. For a service provider, It's a huge advantage for the BNG user plane to be able to automatically scale in and out to meet the required demand. This allows the resources that are not currently being used to be released, maybe put into a low power state used for another function, or even turned off entirely. This means that power is no longer being wasted, keeping the full capacity available for the highest peaks in demand, even during the times of lowest usage.
In this demonstration, we show BNG user plane pod auto-scaling when traffic load varies with time. Here we leverage Kubernetes horizontal pod autoscaler, which implements closed-loop mechanism to periodically monitor the traffic load and scales the number of BNG user plane pods in and out as a result. For metric collections, Prometheus is configured to collect traffic stats, and Prometheus adapter is used to expose collected stats to Autopod Scaler through the Kubernetes custom metric API. A horizontal pod autoscaler continuously observes the traffic load, and when average traffic load becomes greater than threshold value, it adds a new BNG user plane pod. UPSF, with the help of BNG controller application, starts migrating some of the subscriber groups that are active on other user plane to new user plane pod by following make before break sequence that we have demonstrated earlier. On the other hand, when subscriber load decreases, the horizontal pod autoscaler computes the number of BNG user plane pods that can handle the traffic and selects the surplus BNG user plane pods for deletion. As a result, UPSF starts migrating subscriber groups from that user plane pod to other user plane pods using make before break mechanism, eventually consolidating the subscriber sessions onto fewer BNG user plane pods. Here on the screen at top right chart, we can see 3 active BNG user planes receiving and processing subscriber traffic. We have Kubernetes horizontal pod autoscaler running and monitoring the traffic stats. As shown in top left panel, for the current traffic load, desired number of BNG user planes is 3, and currently we can see 3 BNG user planes are running. As per the configuration, BNG user planes can scale up to 5 instances during peak time when traffic load is high, and scale down to 1 instance during off-peak time. On the bottom right corner, we can see power consumption of the platform running the BNG user planes. First, we gradually increase the input traffic to each of the 3 BNG user planes. If you see the bottom left chart, the average traffic per user plane is increasing. At this stage, the average traffic per user plane is greater than the threshold value. On the top left chart, we see desired replica count has now become 4. Now the Kubernetes creates one new BNG user plane pod, and we can see current replica count is increased to 4 now. With the addition of new user plane, the average traffic per user plane again falls below the threshold value. At this point, UPSF starts make before break sequence for moving subscriber groups from currently active user planes to new user plane. And now we can see new BNG user plane is sharing the traffic load with previously running user planes. On the bottom right panel, we see an increase in platform power consumption with the addition of new user plane. Now we gradually reduce the input traffic to each of the 4 BNG user planes, and we can see on the bottom left chart, the average traffic per user plane is decreasing. On top left chart, we can see the desired replica count is decreased to 3 now, and the horizontal pod autoscaler marks one BNG user plane instance for deletion. At this point, UPSF starts make before break sequence for moving subscriber groups from this user plane to other user planes. At this point, all subscriber groups have been moved. On the top left panel, we can see the number of active user plane instances is reduced to 3. On the bottom right panel, we see platform power consumption goes down after deleting the user plane. In this demonstration, we have seen that Kubernetes horizontal pod autoscaler helps in tuning the number of VNG user plane instances, thus optimizes the power consumption when subscriber traffic varies with time.
The demonstrations we've shown are of a real disaggregated cloud-native BNG being maintained, upgraded, and scaled on demand, all without dropping a single customer packet. For an end user, this means that the broadband network is more available, can rapidly react to changes in demand, and is able to steer your session to the most appropriate user plane for your service needs. As a service provider, it enables true cloud-native deployment of broadband user planes using standard Kubernetes capabilities. Patches and features can be deployed at a higher cadence in an automated way and with zero customer packet loss. Network capacity can be scaled automatically to meet demand, reducing energy consumption at times of low load and easily supporting even unexpected demands. That's it for this demonstration. A quick thanks to everyone contributing at the BBF to the architecture for subscriber session steering, and special thanks to Vodafone, Intel and BISTN for their work on these demonstrations.